Good morning, Precalc. Check out this do now. We're going to describe the transformation from that black function graph to the red function graph. And we want to focus our attention on point A as our basis of comparison from the black point A to the red point A prime. Three things we're looking for, so be as specific as possible. Ready, go. All right, well, those three differences are that point A was shifted to the right by 2 spaces. It was then shifted down 4 spaces, and that gives us our new location of the vertex, we'll call it. And lastly, we can see the shape of that V is different. It has gone from like this in the black one to like this in the red one. 3 times taller. We're going to use point B to help us see this. The width between point A and point B does not change in the black one and the red one each time. The width sideways is only 1 space from point A to point B. So we know it's only the height that's changed. And in the red function graph, 3 times taller to get from point A prime up to point B prime. All right, hey, we're looking at function transformations, and our goal today, our learning target, is we'll be able to use properties of translating functions to be able to write. I said new equations and graphs, but really we're just going to focus on the new graphs, and also coordinates. So the other day, I asked you to print out one of these partially completed notes sheets, and then I asked you to go ahead and write in the rest of the notes under the note sheet. So we want to take a look at those and figure out what they mean for us and how we put them into use. Before we do that, I do want to make a couple of notes about my notes. So on the note sheet, I highlighted things using 2 colors. I used yellow to indicate the vertical transformations. So there's different types of transformations, and they're all listed on the note sheet. Everything that affects the function vertically, only affects the vertical aspect of it. It's not like, oh, this transformation does this thing to the vertical part and that thing to the horizontal part all the same. It's like it doesn't work that way. It just affects the vertical. So I highlighted those in yellow, and in the middle column where the function notation is, we'll look the location of the transformation in the equation. That's always going to be outside the function notation, outside the parentheses, and it's only going to affect the y coordinate. So in that third column of our notes page where we see how to change the coordinates, this transformation will only have an effect on the y coordinate. So whatever the x coordinate was, it's going to remain unchanged. And then all of the horizontal transformations I highlighted in green, and in the center column where the function notation is, we'll see these function transformations appear inside the parentheses of the function notation. And lastly, in that third column, the effect on the coordinate, these horizontal changes are only going to affect the x coordinate. So the y will remain unchanged if there's only a horizontal transformation. And then I did also put some asterisks on there. There are a couple places I put these big red asterisks. That's a visual reminder to myself that something especially tricky is happening here. Usually it means the operation that I need to do on the coordinates is backwards somehow from what I see in the function notation. So let's take a look. Here is what the note sheet looks like. So we got vertical translations, and in the function notation, we're going to see that as either a plus d or a minus d. That d would be a number, and it's outside of the function notation parentheses. Whatever that plus d or minus d is, we're going to do that operation to find our new y coordinate. So take the original y coordinate and either add that y coordinate plus the d number or subtract it, depending on what the function notation says. Okay, for a horizontal translation, to slide that graph either left or right, we're going to see a minus c or a plus c inside the function notation parentheses. And if it says minus c in the function notation, that's going to actually move the graph to the right. If it says plus c, it's going to move it to the left by c spaces. And again, you see the first of the red asterisks here. So as a note to myself to make sure I pay attention to what's going on, the function notation, if it says minus c, I do not subtract to find the new coordinate. I need to do the opposite operation. So instead of subtracting c to get that coordinate, I'm actually going to be adding c to move the coordinates of the point to the right on the graph. And if it says plus c in the function notation, I'm actually not adding to find my new coordinate and do the opposite, which is to subtract the old x coordinate, or the original x coordinate, minus that c number. Even though the function notation says plus, I subtract, and that's how I get my new coordinates. Okay, well, we do also have some compressions and stretches. So that's next. This is a vertical stretch or a vertical compression. It just changes the height to either stretch it taller if the a number we see there in front of the function notation, a multiplied by f of x. If that a number is a greater than 1, it's going to stretch the graph to make it taller by giving it a bigger y coordinate. If that a number is something less than 1, like between 0 and 1, it's going to, like a fraction, it's going to squish the y coordinate or make the y coordinate smaller, so the graph will appear shorter. We do what the function notation says onto the y coordinate. So take the old y coordinate, multiply by whatever that a number is, whether it's a big number or a number less than 1, doesn't matter. Just multiply the y coordinate by that number. Okay, next is a vertical flip or vertical reflection. Flip is not something that everyone understands to mean exactly the same thing. So the actual name is reflection, although many people describe it as a flip. Okay, so we're going to see that in the function notation as a negative sign outside before the function notation. And on the notes page, I separated the previous transformation, vertical stretch and compression, because it has a different name. I separated that from the reflection. But in real life, usually these are combined. So the a number can be a negative coefficient. That's fine. We don't need to like do the math separately for the negative sign and separately for that multiplication. You just would multiply by a negative number if that's what showed up. But on the notes page, I wanted to describe them because they have different names. And so I separated them just for that reason. So again, if you have a negative sign in the front, a function notation, that's like multiplying by -1. So you just take your y coordinate and multiply it by -1, which results in having the opposite sign. Okay, moving on to horizontal stretch and compression. So this is probably the trickiest one out of all of these transformations. So we're going to see this as a k, some number k, being multiplied inside the parentheses. It'll be multiplied onto the x. And if that k number is a number larger than 1, sorry, I'm going out of order. If that k number is less than 1, if it's like a fraction or a decimal maybe, if it's less than 1, between 0 and 1, that's going to stretch the graph to make it wider. Okay, which kind of has the same appearance as if we compress vertically, if we make it shorter, that has the appearance to our eyeball of wide. But these two functions transformations are actually different, because this one we're looking at right here is going to take the x coordinate and actually change the x coordinate. So we're taking points that were like, say, here, and we're going to make them farther away from the y-axis. So it actually will change the width. And then if the k number is greater than 1, that makes the graph skinnier. And so it's kind of backwards. You think small numbers makes the graph wide and big numbers makes the graph skinny. That's backwards. And so everything that's inside the parentheses, we end up doing a backwards operation. So if the function transformation in the function notation, if it shows multiplying by k, when we get to the part where we need to find the new coordinates, we don't multiply by k. We multiply by the reciprocal of k, which basically is the same thing as dividing by k. And so division is the opposite of multiplication. Just like multiplying by a reciprocal, it's mathematically equivalent to division, right? So usually it's a little bit more straightforward if we work with the reciprocals. We'll see what that looks like in just a second. And then the last one, it was a horizontal flip or a reflection across the y-axis. So it's flipping horizontally. Actual name is reflection, but again, many people describe it as a flip, and that could be helpful. So the way we see that in the function notation is a negative sign, or a -1 being multiplied onto the x, which is inside those function notation parentheses. And what that does to the coordinates in the third column over there is it just takes the original x coordinate multiplied by -1. So we're going to change the sign to have the opposite sign. And same as what I said before with the vertical Horizontal reflections and horizontal stretch compression, those are often combined in real life. So I separated them on the note sheet just so we can have the separate name and the separate description. But a lot of times, if there is a negative sign for a horizontal flip or horizontal reflection, you're going to see that combined with a horizontal stretch or compression. So you can have a negative coefficient there. That's fine. We don't like separate the negative sign and the K value and do the math separately. It's only just described separately for the sake of getting different names and descriptions. You just do it all together if we're doing the coordinates, and we'll see that again in just a minute. All right, let's take a look at how these transformations affect some coordinates. So I'm going to start at the top here. So my function is described as this transformation, f of x minus 7. I'm given some original coordinates, 2, -6, and I need to find the new coordinates after the transformation is performed. So this is going to be a vertical transformation. It's outside the function notation, and I'm going to subtract 7 from the original y coordinate. So the new y coordinate is going to be -13. And the x coordinate used to be 2. That is not affected by anything that we've just done. So the x coordinate stays as a 2. Okay, next transformation. This function transformation, f of x plus 2. Inside the parentheses, we've got that plus 2. And inside the parentheses is always going to have a horizontal effect. It's going to change the x coordinate. And I remember from my notes page, I always do the opposite sign. So the function notation here says x plus 2, but I actually need to subtract that 2 to get my new coordinate. So I'm going to take the 2 in the coordinates, subtract that 2 from the transformation. 2 minus 2 is 0. And the y coordinate is not affected at all. So that's going to remain as -6. Next, let's scroll a little bit so we can see this. Have a negative f of x. It's outside the function notation, so this is going to only affect the y coordinate. It's a vertical transformation, so I'm just going to take that original y coordinate of -6 and multiply it by the -1 in the function notation, and that will give me +6 as the y coordinate. Right, that x coordinate of 2, not affected at all, so it's going to remain exactly as it was. Next, f of -x. So this time I've got that negative coefficient inside the function notation parentheses. So this is going to affect the x coordinate. It's going to give it the opposite sign. I'm just going to take that 2 and the coordinates multiply by the -1 in the function notation. So my new x coordinate will be -2. The y coordinate of -6 is unaffected by what I've just done, and so it will remain unchanged as a -6. Hey, so let's look at an example of some stretches and compressions. Same directions here, give the new coordinates after the transformation indicated. So this transformation, we got 5 f of x, and of course that means multiplication. We don't always write the times. Usually we don't write the multiplication symbol, but that is 5 multiplied by the f of x. And since it is outside the function notation, I know that's going to be a vertical transformation. It will affect only the y coordinate, and y coordinate transformations, pretty much you always do the face value. It says multiply by 5. I'm going to take that original y coordinate of -5, and I'm going to multiply it times 5. So it's going to give me a y coordinate of -25. The x coordinate here is totally unaffected. This transformation has nothing to do with the x coordinate, so it's going to stay 12. Next, f of 4x. So inside the parentheses, we got that 4x. I know that inside the parentheses is going to be a horizontal transformation, and it will affect the x coordinate. But this is a little bit tricky, right? So let's go back and check our notes to see anytime you can't figure out, like, I don't know what that transformation is, I don't remember, or I want to make sure I'm doing this the right way. So we're looking for f of number times x, where that number is inside the parentheses with the x. So we jump back here to our notes page, and I can see it right. Oh, this one. There it is. So we've got that number. It's called a k on the notes, but that number multiplied by x inside the parentheses. So what I'm supposed to do is take that k, and I need to get the reciprocal. So my number was 4, so I'm going to do the reciprocal of 4. That's 1/4. That is what I multiply to find my new x coordinate. So let's see what that's going to look like for us. Okay, so out of the function notation, the k number, that's my coefficient, that's 4. I need to get the reciprocal. The reciprocal of 4 is 1/4. Now I'm going to take that original x coordinate of 12, multiply it by this reciprocal, the reciprocal of the k value, and 12 times 1/4 is 12/4, or 3. That is my new x coordinate. So the transformation is going to give me an x coordinate of 3. The y coordinate this time is unaffected by this transformation. There was no other transformation that's outside the parentheses. So the y coordinate is going to stay as a -5. All right, here's an example from the WAMAP assignment. On the left side here, I've got some original graph. The graph of y equals f of x is shown. I'm going to do a transformation. So here on the right side, draw the graph of g of x equals f of x plus 2 on the graph below. Okay, so inside the parentheses, we got plus 2. Plus 2 on the inside is just like right here on our notes page. Plus some number c is going to move the graph to the left. If I wanted to think about what's going to actually happen to the coordinates, I'm going to take the original coordinate and subtract that c number out of the function notation. So I could find the coordinates of each of these 3 kind of like ends, the endpoints of each of those segments on the original graph. I could find the coordinates of those, subtract 2 from each of the x coordinates. Okay, that's one approach. I'm not asked for the actual coordinates here. I just need to make that new graph. So the first point on the original graph is at -4, 0. So in my new graph, I'm going to take that, what that point would be, except slide to the left 2 spaces, click. So there's my first point. The next point on the original graph here is at -3, 3. So if I move that left 2 spaces, it's going to be at -5, 3. It's -5, 3, click. And then the last point here on the original graph is at 3, -1. If I subtract 2 from that x coordinate, it's going to be 1, -1. Click. All right. And so the graph, it's got this like tail that follows my mouse around. It doesn't affect anything. I mean, I can see it. It doesn't affect my answer at all. So I can leave that there and just hit submit. It doesn't matter what that point is doing, whether it's doing something or not doing something. If you want it to go away so that it doesn't show up anymore, you can click on that last dot you drew again, which is a little bit tricky because if you miss, it's going to draw another dot, and then that'll be a mistake. You can also just click off of the graph, boop, and now that I have clicked off the graph, it's not going to follow my pencil around anymore. Hit submit. There we are. Here's our next example. We got y equals f of x. Is the original graph shown here. This is on the top part of the graph, and I'm asked on the next graph down below that to plot y equals f of -x. All right, so the -x, that's inside the parentheses. I want to check with my notes page, see what that looks like. Oh, here at the very, very bottom, it's the horizontal flip. I'm going to reflect horizontally across the y-axis. So I recognize that in the center column here, inside the parentheses, you got -x. That negative sign could be part of a negative coefficient. In this problem, it's not. It's just a negative sign. And so what I need to do is change the sign of all of the x coordinates. And what the effect on the graph is it's going to reflect across the y-axis, and Anything that was on the left will end up on the right. Anything that was on the right is going to end up on the left. So this first point here is at -1, 7. I'm going to change the sign of the x coordinate. So it'll be +1, 7. So on my new graph, +1, 7, click. And it says the graph's going to follow me around. So the next point on this top graph is at 4, 4. Change the x coordinate. So it'll be -4, 4, click. Next point in the little zigzaggy shape here, that's at 5, 6. Change the coordinate of the x coordinate to negative, so it's going to be -5 and +6. Click. And then the last point here is at 6, 1. Change the value of the sign of the x coordinate, so it'll be -6, 1. Click. All right, so I've got my shape. I'm going to go ahead and click off the graph so that stops following my cursor around. And then I also need to pay attention to the dots. This graph has some dots. So I've got 2 different styles of dot. I've got a closed dot and an open dot. So this is going to help me identify which point is which when that reflection happens. Like thumb is different than pinky, right? So I want to know which one is which. So the closed dot was at the -1, 7. So I need to draw a dot. Closed dot is dot. I'm going to put that here at the +1, 7. And then at the other end at 6, 1 in the original graph, or -6, 1 is an open dot. So I could click open dot and it will draw that for me. Hooray!